EGR131 Chapter 9. In this video, we will continue to talk about the key concepts of Chapter 9. And as we know, in Chapter 9, we will introduce four important network theorems to analyze the complex the network. In this video, we will continue to talk about the Norton Theorem and the maximum power transfer theorem. If you have textbook, we will talk about the example 9.12 and the example 9.15. Yeah. Let us look at the Norton Theorem first. You have found that for the Norton Theorem is actually be a dual of the Thevenin equivalent the theorem. Okay. The Norton Theorem said any the linear the network like all the DC network we have so far or be this type of the network. So any like the two-terminal DC network we talk about can be replaced by an equivalent circuits. We call this one Norton equivalent circuits. These circuits just include one current source and one parallel resistor. Okay, so here first what we need to do is we need to remove the portion of the network across which the Norton equivalent circuit is found. Okay, so if we look at the example we have here, so for this the circuits we want to find the Norton equivalent circuits for the circuits inside the blue box. Okay, so we have two terminal A and B. So this RL, this R here, RL here is kind of be the portion we need to remove from the network first. Okay, this will be the network we get. We remove the portion of the network outside of the blue box. Okay, the blue box is the circuits we want to find the equivalent of the circuits. So we remove the part of the circuits outside of the blue box. And the second step is we mark the terminal of the remaining two-terminal network. So we need to mark the terminal A and the terminal B. And we said, okay, we will try to find the Norton equivalent the circuits across these two terminals for the circuits inside of the blue box. Okay, so here inside of the blue box we get the Norton equivalent the circuits. So what we need to do is we need to find the parallel resistor Rn, and we also need to find the the current source. We call this one In and Rn. The N means Norton. Okay. So first, how we found the Rn? You have found that the way we found the Rn is actually same with the way we found the RTH. First, we need to set all source to 0. If we get a voltage source, we will replace the voltage source with a short circuit. If we get a current source, we will replace the current source with an open circuit. And then after we do this, we found the result, the resistance between these two marked the terminal. Okay, and then how we found the In. We also call this In ISC. So the SC means short circuit. So what we need to do is first we returning all the source to their original position, and then we need to find in the short circuit currents between the marked terminal. Okay, the short circuit current is the In we talk about. Okay. Okay, so if you want to use an ammeter to check it, you could just put an ammeter between that to mark the terminal. And that kind of the way we check the In for the circuits we have in if we have the lab. Okay, so the conclusion is after we get the In and Rn, we could put the portion back. The portion we remove the RL part back to these circuits, and we could draw the Norton equivalent circuits with the portion of the circuits previously removed. Okay, between the two terminals of the equivalent the circuits. Okay, so here I show you the relationship between the Norton theorem and the Thevenin equivalent theorem. So you could see if you use the way the circuit analysis method in chapter 8, we do the source conversion. So you could see the voltage source in series with one resistor could be equivalent to a current source in parallel with one resistor. So for one circuit, we could find both the Thevenin equivalent circuits and the Norton equivalent circuits, and you could find that these two equivalent circuits they actually kind of be the source conversion. Okay, if you have voltage source ETH and one like the series resistor RTH, and you have a current source like the IN, and you have a parallel resistor RN with this current source, they actually have this relationship. First, the RTH is equal to RN, okay, and then the ETH equal to IN multiplied with RN. That is the same with that this IN will equal to ETH over RTH. Okay, so you could see here is the positive terminal and the currents will go up. So you see, okay, you could find the direction of the current source and the polarity of the voltage source, they also match. Okay, so let us look at the example 9.12. So if you check, this circuit is actually same with the example for our Thevenin equivalent theorem, the example 9.6. Okay, so we need to find the Norton equivalent circuits for the circuits inside the blue box. So what we need to do is, first we remove the part outside of the blue box. We remove the RN, and then we mark the two terminal A and B. So here is the network we get. Okay, and then the second step is we need to find the RN. To find the RN, first we need to set all the power source to 0. In this circuit, we just have a voltage source, so we just replace the voltage source with a short circuit. Okay, and then we found the resistance between these two terminals. Okay, between these two terminal A and B. So if you get out from the terminal A, so you could see your R1 and R2, they are in parallel. So you're supposed to have 3 ohm and 6 ohm in parallel. So that will be 2 ohm. Okay, you found your Rn equal to 2 ohm. Okay, that is the first step. You found the Rn. And then you need to find the IN. So to find the IN, you just need to place a short circuit between these two terminals. Okay, like what I do here, you place a short circuit here, and to identify the direction of your IN is from the point A to the point B. So you need to find what is your IN. For these circuits, if you put a short circuit between the AB, and then no currents will go through your I2. Okay, when the currents get out from the power source, they go to this point, you found they will go through these short circuits because the resistance is kind of like the traffic. If you found one road have a traffic, okay, if you drive your car, you will try to find a road that don't have any the traffic here. So the current is kind of same. They we will say this R2 is short out. So it's shorted out. So the currents will go through this short circuits and then go back to the active terminal. So if you check that, you will find that your circuit is just like a series circuit, just have one power source and R1. So the currents here, IN will equal to 9 volt over this is 3 ohm. Okay, you see one current, the I1, also the IN goes through this the series, the closed loop. So 9 volt over 3 ohm, you get a 3 ampere here. So you found the Norton equivalent the circuits like this. So what the next step is you need to do is you draw your the circuits. So let me double check. Okay, so you see your currents supposed to go up. because only when your currents go up and then the currents will for the terminal A and B, the currents will go down, like what you draw here. So for example, if you get the ion here is negative value, so like the direction of your current source might be go down. Okay, just pay attention. So you draw your the Norton equivalent, the circuits. The ion is equal to 3 ampere is from this circuit, and your Rn is equal to 2O is from this circuit. And then you put your RL back. Okay, so this circuit is the Norton equivalent circuits for these original circuits. Okay, so you could see for these two circuits, the part inside the blue box, they are different. Okay, the part inside the blue box is different, but the portion outside of the blue box, the RL part, they are same. The voltage across the RL, the currents go through this RL, were all same with the original circuits. Okay. But if you want to find, okay, what is the currents go through this R1, or what is the currents go through the R2, you need to go back to the original circuits. Okay, you could use the result you get here. Okay, you know the voltage across AB is the same with here. You know the currents here. Okay, but you need to go back to the original circuits to find the currents, the voltage for the R1 and R2, because in your equivalent circuits, you don't have R1, R2, you don't have the E here. Okay, so everything inside the blue box will be different, the voltage, the currents. Okay, you cannot find the voltage and the currents here in this equivalent the circuits, but all the things outside of the blue box, they are same. So you could use the equivalent circuits to find the voltage across this RL and the currents go through this RL because they are equivalent. Okay, so outside the blue box, the voltage and the currents are the same. Okay, so here I also give you the source conversion. So if you know how to find the Norton theorem, like the Norton equivalent circuits, you could quite easy to find the Thevenin equivalent circuits. The ETH will equal to IM multiplied with Rn, 3 ampere multiplied with 2O. So you will get the ETH will equal to 6 volt, and your RTH equal to Rn will equal to 2O. Okay, so the currents go up. So here should be positive terminal, and then the currents will go up. Okay. Okay, that is the Norton equivalent, the circuits. I hope you totally understand these circuits. You need to understand, okay, here, like for this example, the circuits inside the blue box is actually very simple, but you could imagine if you have very, very complex the circuits, you also could do something like this. Okay, and then your circuits will be the simplest, the parallel circuits. You could analyze the equivalent circuits very easy. Okay. Okay, let us look at the second key concept in this video is the maximum power transfer theorem. When we design a circuit, we always want to find for what load we could receive the maximum power from the system, or what condition like we could ensure the source can deliver the maximum power available. Okay, for this maximum power transfer theorem, we talk about the first type of the problem. So what load could get the maximum power from the system? Okay, so the maximum power transfer theorem is actually very easy. If you already get the Thevenin equivalent the circuits for your like the network, okay, and then your load need to equal to the resistance of your load need to equal to the RTH. Okay, if you already get the Norton equivalent circuits for your network, same thing here, your load equal to the Norton equivalent the resistance, then your RL will get the maximum power. Okay, so the maximum power transfer theorem is kind of answer the first the question, what load should be applied to a system to ensure that the node is receiving maximum power from the system? Okay, so you can see here I give you two plot. Okay, this two plot is actually same thing, but one these x-axis have like the RL, like you see have the evening scale here, but for the second one they have the log scale here. Okay, you don't need to pay too much attention to these two plot. You just need to know they actually be the same plot. We just try to plot the circuits like this. So you could see when your RL is smaller, then the voltage across this RL will be smaller, but the currents will be bigger, because in these circuits the total the resistance will be smaller, so your IL will be smaller. So it's kind of at the beginning the IL is the maximum number, and when your RL go bigger and bigger, then your IL is always decrease. Okay, but your VL, you see at the beginning is a very small number. When your IL is go bigger, this VL will increase. Okay, so your IL will decrease and your VL will increase, but your PL is equal to IL multiplied with VL. So you could see they will increase first and then achieve the maximum number and then decrease. Okay, it's kind of like the plot we have here. They will increase first and drop then. So we will have one like the RL could make we get the maximum power. In this example, your RL is equal to RTH is equal to like 9 here. Okay, so let us look at this here. We have the example 9.15. Okay, so what we need to know is, you see we have three different type of the circuits. We have like is 120 volt RINT. Is kind of like the internal the resistance for this the power source, and we have this node, and we have a battery. For the battery, we also have the internal the resistance for this the battery, and we connect the RL, and we could have the laboratory the power supply. The voltage is from 0 to 40 volt, and we have in like the internal the resistance is 20 ohm. So for this three example, you need to know to achieve the maximum power. So you need to make the RL equal to the RNT is 2.5 ohm, and your RL here is equal to 0.5 ohm. Your RL here equal to 20 ohm. Okay, you could think you already get the Thevenin equivalent the circuits. You have one power source in series with one resistor. Okay, here the INT is kind of same with the RTH. You need to make your RL equal to your RTH. Okay, so when you get the RL equal to 2.5, 0.5, and 20 ohm, and then you could find the maximum power. So I give you two equations here. So they actually same, because you are like the if you get the Thevenin equivalent the circuits, the ETH is actually equal to the IN multiplied with RN, and you also have RTH equal to RN. So if you substitute these two the equation to this the equation, you will get the same the equation the second the equations here. So they actually be same. Okay, so for this example here, the PLMAX, okay, we kind of think the E is our ETH here, 120 volts square over 4 RTH. RTH is 2.5 ohm here. Okay, this will be our maximum power. Okay, for the second example, we will get PLMAX will equal to the E is 12 volt square, ETH square. For RTH here is kind of 0.5 ohm. Okay, for the last example, PLMAX will equal to so the E here you have here So it could be any number between 0 to 40 volt. Square over your full RTH is RNT here, 20 ohm here. Then you could get the maximum power you could get from the RL. So don't think too much about the maximum power transfer theorem. Okay, try to get the Thevenin equivalent of the circuits or the Norton equivalent of the circuits first, and then your RL just equal to the RTH. Okay, then you will get the maximum power for your like the load. Okay, so after this chapter 9, you need to be totally understand this for the theorem. Okay, the superposition theorem, the Thevenin theorem, and the Norton equivalent of the theorem, and the maximum power transfer theorem. Our final exam will be like this. Will be a little bit difficult than the simplest the example we have for this chapter. You might need to use something you already learned from chapter 1 to chapter 8. We will have the practical the examples for your final exam for our next week. So if you get some time, you could check that the practical final exam in this week and prepare for your final. So that's it.